Hello everyone, welcome back, and I hope you're doing well, and I hope your journey with these econometrics lessons are also going well. So let's just move ahead. So we are moving very slowly, and I hope you're understanding whatever is being delivered. So let's move ahead. So today we'll be talking about the extension of the two variable regression model. Okay, so we'll see what this means and why we are doing this. So, okay, let me take this color. So we'll be talking about here extensions of the two variable linear regression model. Okay, so we have different extensions, so we'll cover them one by one. So the first variation or your extension is called the regression through the origin. Regression through the origin. So when the regression line passes through the origin, which means that your beta 1 is equal to 0. So how do we deal with such regression lines? How is there a variation in the beta 2 hat or the estimators of the parameters, how they vary? Okay, or how the formulas through which we estimate these parameters, they vary. So we'll see what changes come to the model once we have a regression line that is passing through the origin. So suppose the population regression function takes this form, which is your yi is equal to beta 2 I xi plus ui. So in here your beta 1 is equal to 0. Your beta 1 is equal to 0. So normally we have beta 1 plus beta 2 xi plus ui. So normally we have this equation, but in a special case where your beta 1 is equal to 0, this term is equal to 0, we get this form wherein yi is equal to beta 2 xi plus ui. So in here we have the intercept form, or the intercept equal to 0. Okay, beta 1 is equal to 0 and beta 1 represents your intercept. So intercept means this part or this part. Uh, how far from the origin is my regression line? Okay, so that is your intercept part. So this is the form where the intercept is equal to 0. So how do we estimate such models? So whenever we have this kind of equation that we're dealing with, how do we estimate the model? How do we estimate the parameters? Okay, so what changes comes in the estimation or the formulas through which we'll be estimating your different values of the parameter. So we have the estimator of beta 2, okay, which is beta 2 hat. Then we have the variance of beta 2 hat. Then we have the estimator of the variance. Okay, so we have seen, so let me move ahead. So we have seen in the traditional form, the formulas for computing my estimators, like my beta 2 hat was summation small xi yi. So we have seen what these notations mean in the previous videos, and you can go back and check in the previous videos. So I hope you're following the previous videos also, so that you have a continuation and understanding of notations, and through which you'll have a proper and better understanding of the videos. So this is small xi, this is small yi, and this is small xi. So these are the formulas for calculating your beta 2 hat in the standard normal regression model. Okay, in the standard form that we had seen in the previous video, or the basic understanding of population regression function or the sample regression function that we had seen. So this is how you calculated the variance of beta 2 hat. Okay, and this was the formula for your sigma hat square. So sigma hat square was the estimator of your sigma square. Okay, in case you don't have this value, you'll have to estimate this value. So you'll be estimating this value with the help of this formula. Okay, this formula, right? So in the case of your intercept form, the formulas change a bit. Okay, since your beta 1 is equal to 0, so the formulas that we get is The first formula is your beta 2 hat is equal to summation capital Xi yi upon capital Xi square. So this is not small xi or small yi. This is your capital Xi yi. Similarly, in the case of variance, we have sigma square upon summation capital Xi square. Okay, so capital X here also capital X and y. Sigma hat square is equal to your ui hat square upon n minus 1. So this is also different. In here we had 2 degrees of freedom, okay? N minus 2 degrees of freedom. Here we have n minus 1 degree of freedom. So 1 degree of freedom is extra here because your beta 1 is equal to 0. So we don't have to estimate this value, and that is why we have a higher degree of freedom here. Okay. Now, what are the features of such functional form functional form of the regression equation, the regression function? So the first feature is that your summation ui hat may not be 0. So if you go and recall the previous videos, we had seen that the assumption that we made of summation ui hat equal to 0 was based, or a lot of it was based on the fact that we had a intercept intercept okay, term, that is your beta 2. So this was helping us a lot to conclude or use this assumption that your summation ui hat is equal to 0. So I hope you remember this. We had also proved this thing, that your summation ui hat is equal to 0 with the help of the intercept term. So in here, since the intercept term is not there, it means that we cannot assume that your summation ui hat is equal to 0. So it may or may not be equal to 0. So this is the first feature of this form. And your r square can be negative here on certain occasions. Okay, so this is also a feature. So your r square can be negative. So we have seen in the previous videos that my r square value lies between 0 and 1. Okay, so in this functional form, it can also be 0, it can also be less than 0 in certain occasions. Okay, so these are a few deviations that we see from the normal regression function that we have seen previously. So this is a special case where your beta 1, sorry, this is beta 1. Okay, beta 1 or intercept term is equal to 0, right? So this was about your regression through origin. So this is one of the extensions. There are other extensions also, or the other deviations or different forms of linear regression models. So we'll see those different models one by one. So this is the first one. So I'll bring up the other models in the upcoming videos. Okay. Till then, take care. See you soon.